let's go ahead, and there's a couple of things I want you to pay attention to. First of all, yesterday we did the main group elements, and the main group elements, of course, were the S block and the P block. The D block is going to be different. So if you want to put up above where you see transition metals, you can put D block up here, because the D blocks are going to be different, okay? The D block is different, okay? No, you're on the right page, okay? It looks just like yesterday. It's just, I put the periodic table on there again because it's easier for you to be able to write on that and look at it. Okay, so here's the thing that's unique and different about your transition metals. Okay, transition metals are going to be different in the fact that they can lose several electrons. Okay, and because they can lose several, that means they don't have one set charge. Like potassium always loses one. It doesn't lose two. It loses one. Oxygen gains two. It doesn't gain one. It doesn't gain three. It gains two. Because once it has a full outer shell, it's done. And it's not going to gain or lose anymore. But transition metals, because they have those D block electrons, you know, they can lose one, they can lose two, they can lose three, they can lose four, they can lose five, they can lose six, they can lose seven. I can't think of anything that loses 8 right now, but maybe there's something that I'm forgetting. But what I need you to understand is that when they lose electrons, they lose them in a certain order. Okay, and this is where you have to be careful, and you may want to put a little star by it to make sure you remember this. They always lose S electrons before D electrons. They have to lose them in that order. They always lose S before the D's. Okay? Always, always, always. So make sure that you're careful when you do that. And I'm going to give you several examples so that we can see. All right? So having said that, let's go ahead and let's look at an example. So I'm going to circle on here. Let's do manganese. Okay, let's do manganese. Now the best way to do this, guys, is to go ahead and do manganese like you normally would. Okay, so manganese, when you would write manganese, you would use argon, and then what would you say after that? What comes after that? Argon, 4s2. What comes next? 3d, how many?
5.
3d5. Good. Okay. Now, that's what manganese is normally. And what I tell students to do is don't try to do it like you did the others, where you kind of worked backwards on the periodic table. Don't do that. Write down what it would be when it's neutral. Because manganese, or any transition metal, can lose different numbers. And I'm going to have to tell you how many it loses. So if it's manganese plus 1, it loses 1 electron. And I just told you, you have to lose which ones first? You have to lose your S before you lose your D. So that's supposed to be an R, sorry. AR. I haven't figured out how the eraser works, so that'll just have to do. So it's AR 4S, and what do you think you're going to put there? 4S1, 3D5. Okay? 4S1, 3D5. If I also gave you, and you can do this down at the bottom or you can do it at the top, it doesn't matter. If I gave you Mn plus 3, that's going to be different. Look at neutral manganese. We've got to take 3 away. But you got to lose your S before you can ever lose your D's. And to me, it's difficult to do it by looking at the periodic table. It's much easier to write it as it would be if it had not lost any, and look at that and then take them away. So what would your electron configuration be if it was Mn plus 3? Argon what? 3d4. Okay? So that's pretty easy. Now, we can have some that it can lose even more than that. Okay? So let's look at another example here when we have some of those. Just come on in. Let's look at, what if we had manganese 7? Thank you. Okay? Mn plus 7. Now, I don't have my sheet in front of me, so you'll have to look at your previous electron configuration. But when you do Mn plus 7, it's going to be argon. And you got to lose 7 electrons. Wasn't it, when it was neutral, it was argon, 4s2. How many Ds were there? 3d5? Okay. So if it's Mn plus 7, it would actually look like argon, wouldn't it? But you can't do that. So what would I do? I would go and do neon, right? And then come after that, do neon, and then what would come next? 3s2, 3p6. That's it. That's all there is to it. Now, I told the last class, and I'll tell you the same thing. Again, this is not something that's hard. It really isn't. But I will have students miss 10 points because they will forget that you have to lose the S before the D. And I understand why students want to work backwards and take from the D because the D is at the end, but that's not what happens. So they have to lose their S electrons first. Does that make sense? Is that pretty easy? Let's do one more just to see. Let's take, let's do Ni plus, let's do Ni plus 3. Y'all do Ni plus 3. Nickels right here. Again, I usually write the whole thing out. Now, last period I had several of them and that were not writing it out neutral, and they were doing it correctly. Just be careful, because sometimes what I've had students do when they do it that way, they actually they do make a lot of mistakes if they're not careful. So what would it be? It would be argon. What would come next? Okay, 3D. I think that's right. Y'all agree? Okay. All right, so just be really careful when you do that. Okay, so you may want to write it neutral first, and then out beside it, go ahead and write it when it loses the electrons, and then you can circle that one. Okay, whatever way it's going to work for you is fine with me. All right, let's look at one more thing that we need to do. Does that make sense? I mean, I can do several more examples, but I think it's most of the time students do pretty well with it. All right, now I need you to take your periodic table here, and I want you to highlight a different group. Let me make it so that you can see it a little bit better, and let me scroll up or down. Hey, y'all talking about electron configurations?
Yeah.
I doubt it. Okay, so let's look at this next one. Let me scroll it down just a little bit so you can see it a little better. Okay, all right, on this particular one, I want you to go ahead and I want you to put a box or square this group right here, chromium's group, and I want you to put a box or square copper's group. There's a reason. Those particular groups don't follow the rules for electron configurations the way we normally would think about it. Okay, so highlight those, and you can put yourself a note that says these are exceptions. For everything that we learn about in chemistry, for every rule, there's at least one exception, sometimes more. Okay, but those are exceptions. Those are exceptions. Now, having said that, let's look at let's look at chromium. Okay, so let me put up, I don't really want that. I want that to go away. There we go. All right, so chromium. All right, so Cr. Let's go ahead and write what it would normally be. Okay, so I'm going to call this expected. And the expected for chromium is argon. What comes next? I think it's argon, isn't it? Yeah, argon 4s2, 3d how many? 3d4. Okay, that's what you would expect it to be. The truth is, that's not what really happens. So I'm going to draw down here the orbital notation. I'm not going to do the whole thing because all I'm doing this for is to explain it. What you normally think is that it would look like this. So 4s would have 2. What would you do with the 3Ds? 4 going up. Now, look at that little lonely d orbital down there at the end. He's sad. Guess what happens? The 4s electron that we normally think would be here, it actually moves right here. Okay? And because it moves right there, that means that the actual is not actually 4s2 3d4. It's actually 4s what? 4s1 3d5. Okay? That is chromium. That's chromium. In fact, if you go back, and I'll go back to my sheet just a second and show you. If you'll go back and look at the one that I had before, well, I thought I could go back. If you go and look at the one below chromium, molybdenum, MO, it would be the exact same thing, except instead of 4s1 3d5, it would be 5s1 4d5. Okay? Now, one that's a little bit tricky is one like tungsten, because students will not know what to do with the F block. So let's do tungsten. Tungsten, the expected, if you do tungsten, it would be, I think tungsten is what? Is it xenon? Okay, Xe, 6s2. Now, you can't forget the 4 Fs. You've got to go through the 4 Fs, so you'd put 4f14, then you'd come back and it'd be 5d4. Okay? But that's not really what happens. And you don't have to draw that out, the orbital notation, but I want to show you that. The actual is actually xenon, and then tell me what it would be when that electron moves. 6s1. What else? 4f14. Don't touch the F's. Do not touch the F's. Okay? Never. And then you're going to get 5d how much? 5d5. Okay, the same would be true if we ended up doing Sg, suborgium. We would have the 5 F's. You still would not touch those. Okay? You would not touch the F's. All right, let's look at one of the ones on the other side. Let's do copper. Cu. If we look at our expected, it would be argon, 4s2, 3d9. If I draw that out, 4s, 3d, it would be up, down, up, 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 down, down, down. One more. Look at the last little orbital there. He just needs one more. So what happens is this little guy moves over here. Okay? So the actual would be argon 4s1 3d10. So any of them that end in s2d4, they become s1d5. Any that end in s2d9, they become s1d10. And if you have one like, I guess it's gold, and you go through the F block, you do the same thing. You just don't mess with the F's, okay? You don't mess with the F's. Now, what I also want you to know is the reason that this works, okay? Why? It's a more stable electron configuration because the S is actually higher in energy and half filled orbitals or filled orbitals are more stable. Sorry, my handwriting's like that, but I'm trying to get used to using a stylus. I'm not used to it. I'm used to using it's a stylus, but it's not. This is like the one that has the little rubber end on it, and it's harder. I'm having to push like really hard. So, anyway. All right, if you would. Does that make sense, guys? Okay. All right, here's what I need you to do. All right, turn it over to page 10. What I think I'd rather you guys do, because last period I actually picked up really quickly on it, I want you to go ahead. I'm not going to work any of these with you. You can look at your periodic table. You can look at your notes. Okay? Work through those. And let's try to check them before you go. Okay?